Hey everybody, in this video we're going to be introducing stoichiometry by essentially explaining what it is by explaining the concept of mole ratios. Let's get started by looking at this reaction shown across the top. CH4, which is methane, combusts or reacts when in the presence of O2, if you give it some heat of course. And when that happens, you produce CO2 and H2O. The first thing you got to know about stoichiometry is that it's all based off of a balanced chemical equation. So before you can even begin to understand this word stoichiometry and what it is, you need to know that you need an equation, and that equation has to be balanced. In this case, because there's 4 hydrogens on the left, I need a coefficient of 2 in front of water to get those same 4 hydrogens. That of course gives me 4 total oxygens on the right, so I need to put a 2 here to get those same 4 oxygens on the left. And just to make the point that there's just one of each of those particles, I'll fill out the coefficient of 1 for CH4 and CO2, although you can technically leave that out. So that's the first important thing. The next important thing is to realize what those numbers mean or represent. Beyond just the fact that they make the equation balanced, what does 1, 2, 1, 2 actually indicate about the particles that are involved in this reaction? And it indicates something really simple that is pretty obvious once you hear it. Those coefficients are literally telling you the number of particles that you need and that will be produced as this reaction happens. In other words, that coefficient of 1 in front of CH4 actually just means that when this reaction happens, there needs to be 1 CH4 to react with every 2 O2s. And that's going to produce 1 single carbon dioxide and also going to produce 2 H2Os. So there's really nothing mysterious about coefficients. They're straight up telling you how many of each particle there are. In these different scenarios, we're going to start to apply those numbers with what about, like it says in scenario 1, what if you were told that there was 1 single CH4 molecule and had to come up with or make a prediction about how many oxygen molecules would you need to react with that 1 CH4. Based off of what we just clarified, you would need exactly 2 oxygen molecules, because that's what the coefficients of 1 and 2 are telling you. This would produce 1 carbon dioxide and 2 water molecules. Those things we just filled out where we made predictions about how much O2 is needed and how much CO2 and water are made, that's what stoichiometry is. It's predicting the quantities of reactants needed and the quantities of products formed based on some amount that you're given. The cool part is you can scale that up to different starting points and different quantities, like in scenario 2, where we are instead told that there's 6 oxygen molecules. If you follow that same 1-to-2 ratio, knowing that there's 6 O2s, you're going to need half as many CH4s, so in this case 3 CH4 molecules to fully react with those 6 oxygen molecules. That of course is going to produce 3 carbon dioxide molecules, because that same 2-to-1 ratio exists between O2 and CO2, and that's going to produce 6 water molecules for the same reason as before. The only other leap that stoichiometry takes is using other words to describe how many particles there are, like dozen, and eventually we'll switch over to moles. So we're going to skip ahead here to scenario 5. In scenario 5, you're not told how many individual CH4 molecules, directly at least. You're told that there's 1 dozen of them. Now that of course means there are 12, but we're going to fill out scenario 5 by using this word dozens instead of counting the individual particles. If there's 12 CH4s, then that of course means we're going to need twice as many O2s because of that 1-to-2 ratio. So I'm going to need 24 CO2s, which in terms of dozens is of course 2 dozen. That's of course going to produce 12 carbon dioxides, otherwise known as 1 dozen, and 24 waters, otherwise known as 2 dozens. And while this might seem silly, it teaches you a really important fact about these coefficients. It teaches you that this 1-to-1-2 ratio works for individual particles, like we saw with scenarios 1 and 2. Let's label that to keep track, right? These coefficients work for individual particles, but those coefficients also seem to work for words like dozen. We'll call them counting units. So now I know anytime I see coefficients like 1 to 2, 1 to 2, I can apply those to terms like dozen. And our final leap for the video is words like mole, because in chemistry we don't count particles in dozens, we count particles in moles. But a mole functions just like a dozen does, it's just much larger. So if we skip ahead to scenario 8, where we're told there's 1 mole of CH4, I could predict that I'll need twice as many, 2 moles of oxygen, based on that 1 to 2 ratio we've been applying this whole time. That's going to produce 1 mole of CO2 and 2 moles of water. And that is the basis for all stoichiometry. That also wraps it up for this video. Thanks a lot for watching.